So for this meeting, our intended learning outcome for this discussion is first to understand the underlying concepts on the design of a prestressed concrete element with respect to flexure. So we will just focus on the design of prestressed concrete elements with respect to flexure on this particular topic that we have. And then after addressing that first goal, our next and final goal for this discussion is to be able to design a prestressed concrete element with respect to flexure. So we will try to design a prestressed concrete element that is adequate enough to resist the flexural stresses that is being experienced by the element itself. So without further ado, let's address our first goal, which is to understand the underlying concepts on the design of prestressed concrete element with respect to flexure. And then after that, let's immediately address our second goal, which is to be able to design a prestressed concrete element with respect to flexure. So we will try to apply the things that we have learned on our first goal to the second goal. So just to give you an introduction about the flexural design of prestressed concrete elements and why we are doing those design. So for our refresher, we know for a fact that the flexural stresses are the result of external or imposed bending moments. So when a concrete element supports an external or imposed loads, those loads tends to produce what we call flexural stresses inside the concrete element itself. So those flexural stresses actually tends uh, to affect the strength of the concrete element. It may tend to degrade the the strength of the concrete element. In most cases, they control the selection of the geometrical dimensions of the prestressed concrete section, regardless of whether it is pretensioned or post-tensioned. So if we will try to design uh, flexural members, usually their design is being controlled by the flexural stresses that are being experienced by the element itself. Obviously, that's why it's called flexural member. So with that, uh, whenever we design flexural members such as beams are flexural members because they usually support or usually resist what we call bending moments. They tend to bend. That's their natural behavior. They tend to bend and resist bending moments. So their design or the selection of the geometrical dimension of that particular prestressed concrete element, is usually dependent on the magnitude of the flexural stresses that are expected to be induced inside the element itself, regardless if it is pretensioned or post-tension. The design process starts with the choice of a preliminary geometry, and by trial and adjustment, it converges to a final section with geometrical details of the concrete cross-section and the sizes and alignments of the pre-stressing strand. So the design of flexural members, especially beams, usually starts with a preliminary geometry. So you cannot start the design of any element, actually any element overall. You cannot start the design, even on actual design. You cannot start the design if you don't have uh, what we call a preliminary geometry or preliminary member size, wherein you will just assign a particular section to a member just to start the design process. So you have to you have to uh, assign preliminary section to start the design process, and then with that, starting from that preliminary section that you have assigned, uh, you will just have to make a what we call trial and adjustment to that particular preliminary section that you have assigned uh, initially until it converge to a final section with geometrical details of the concrete cross-section and the sizes and alignments of the pre-stressing strands that can address the effect of the flexural stresses that will be induced on the flexural members such as beams. So actually that is a basic knowledge on the design process. We usually start the design process with a preliminary section, and then with that section will just undergo what we call trial and adjustment, wherein we have to check the adequacy of that particular preliminary section that we have assigned initially until we have found a final section with geometrical details that will address the the demand from the applied loads that are being carried by the prestressed concrete element that we are designing. So usually the assigning of those preliminary sections usually requires a what we call enough experience in terms of the actual design. That the selection of the mag of that particular preliminary section usually requires experience. So usually the people that usually assign those preliminary sections are the people that have a wide range of experience in terms of designing. So they actually design already many different structures wherein they already know what particular section can be adequately support a particular demand or load that is supposedly being carried by the element that we are supposed to design. And then uh, the section satisfies the flexural or bending requirements of the concrete stress and steel stress limitations. That just like what I have said a while ago. So again, starting from that preliminary section that will undergo a trial and adjustment until it converge to a final section with geometrical details that must satisfy the flexural or bending requirements of the concrete stress as well as the steel stress limitations, because as you can remember from our previous discussions, the code specifies a certain magnitude of concrete stress and steel stress that it permits to be experienced by the concrete and steel reinforcements respectively. So the reason for that is because the code doesn't want the materials, the concrete and the steel, to experience overstressing. That's why it just limits the stress that can be permitted to be experienced by the concrete and steel to a certain magnitude. So you can just refer on the specific provisions on the code if you want to be familiar with those particular maximum permissible stresses for concrete and steel. Thereafter, other factors such as shear and torsion capacity, deflection, and cracking are analyzed and satisfied. So after you have a final section that satisfies the flexural or bending requirements of concrete stress and steel stress limitations, after you have that final section, you have to check as well the other factors such as shear and torsion capacity, deflection, and cracking on that particular section that you have found uh, from initially satisfying the flexural or bending requirements of the concrete stress and steel stress limitations. So the the precise concrete element that you are designing must not only satisfy the flexural requirements, but it must also satisfy the other requirements such as the requirements for shear and torsion capacity, meaning your pre-stressed concrete element must not only be able to resist flexural stresses, but as well as the shear stresses and torsional stresses that may be induced on the concrete element that you are designing as it serves its intended purpose, as well as the deflection and cracking that is expected to be experienced by the element that you are designing. So you have to control the magnitude you have to control the magnitude of the deflection that that is permitted to be experienced by the concrete element that you are designing. So actually, those are just the basics of design with respect to pre-stress concrete design. So we just have to satisfy certain criteria, s- especially the flexural criteria, the shear and torsion criteria, as well as the deflection criteria. So we just have to satisfy all of those criteria for us to have a final design of the element that we are designing. So uh, we just with that let us just compare the design of reinforced concrete to the design of prestressed concrete uh, elements. So let us see, or let us take a look what what are the differences between the design of reinforced concrete and the design of prestressed concrete. So it suffices in the flexural design of prestressed concrete members to apply only the limit states of stress at failure for the choice of the section, provided that other requirements such as serviceability, shear capacity, and bond are met. So this comparison is actually limited to the flexural design of both reinforced concrete and prestressed concrete. So for the case of the flexural design of reinforced concrete members, we just usually satisfy the limit state of stress at failure for the choice of the section, meaning our design is just usually dependent on the limit state of stress at failure, meaning we are just searching for a particular section that can withstand the stresses that may be induced at failure due to the application of the loads that are expected to be carried by our flexural member. So that is usually the basis or the limit state that we just usually check for the design of reinforced concrete. So we just usually check the adequacy of a certain section to resist the stresses at failure, meaning the reinforced concrete will already experience cracking and impending failure, meaning total failure, as in the flexural member uh, may may already disintegrate, or although we can actually say that failure already occurred if the steel reinforcements for a reinforced concrete already yield, as well as the concrete itself. So actually, when we say failure, we usually has I mean we usually have a basis for us to say that a material or a member already failed. So for the case of reinforced concrete, in terms of the design of reinforced concrete, we usually say that the design of the reinforced concrete already failed if the steel reinforcements already yielded, as well as the corresponding concrete component. So for the reinforced concrete design, we just check the capacity of the section at failure. For the case of the design of, or I mean, for the case of the flexural design of reinforced concrete, we just check the capacity of the section at failure. But in the design of pre-stressed members, however, additional checks are needed at the load transfer and limit uh, state at service load, as well as the limit state at failure. with the failure load indicating the reserve strength for overload conditions. All these checks are necessary to ensure that at service load, cracking is negligible and the long-term effects on deflection or camber are well controlled. So unlike for the flexural design of reinforced concrete members, which wherein we just check the the capacity of the section at failure, for the case of pre-stressed members, we don't just check the capacity of the section at failure, but there is actually what we call additional checks that we usually do for the design of pre-stress members, and those checks actually happen on the load transfer, wherein the pre-stressing force is already transferred to the concrete element, as well as the limit state at service load. So we are checking as well some criteria on this particular stage of pre-stressing, not only on the stage of not only on the stage of the life of pre-stress member wherein it will already experience failure. So we know for a fact for the case of uh, both members, reinforced concrete members and pre-stress members, we know for a fact that these these members will experience degradation as it supports loads. So the final point on the life of a member, either reinforced concrete or pre-stressed concrete members, is the failure part or failure stage, wherein the members that we are designing already experiences failure. So again, when we say failure, it not necessarily mean that the member already broken into pieces, but we are just telling that they already failed to satisfy certain criteria that uh, we have we want them to satisfy. So usually those criteria is for the case, for example, of the reinforced concrete design. We usually say that it already failed when the steel reinforcement already yielded. And then for the case of pre-stressed members, actually we have the same criteria. We also says that the at the final stage of life of the pre-stressed members, we also say that it already failed when the steel reinforcement as well as the pre-stressing reinforcement already experience yielding. But in addition to that criteria that we are checking for the design of pre-stressed concrete members, we are conducting additional checks, which are the checks happening at load transfer and the checks happening on the service load condition. So at load transfer, uh, we are checking if the stresses acting on the concrete element itself is already, I mean, we are checking that the load stresses acting on the concrete element that we are designing are still conforming to the code limitations at load transfer. That's why, if you can remember from our previous discussions, we studied the maximum permissible stress specified by the code for, say, for example, for uh, at transfer stage and then at service load condition. So we are not only satisfying the limit state at failure, but we must also satisfy the code requirements for load transfer and at the service load condition. So we also have to check the corresponding stresses that will be induced to the pre-stress member that we are designing at load transfer and at service load condition. So those stresses must not exceed the maximum permissible stresses specified by the code for load transfer stage as well as at the service load condition. And then ultimately, the pre-stress member must also satisfy the limit state at failure, wherein it must not experience yielding with respect to the steel reinforcement or the pre-stressing reinforcement. Actually, the 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 limit state at failure design of prestressed concrete members are somewhat or somehow similar to the design of the reinforced concrete members at the limit state of uh, stress at failure. So usually they just have a somehow similar procedure, some similar formulas for the design at failure, or the what we call the ultimate strength design. So usually they just have a uh, same formulas and same procedures for the design at ultimate strength. So the only difference with them is that for the case of pre-stress members, there are actually additional checks that we are doing, which are again the checks of the stresses being experienced by the concrete as well as the steel, as are the pre-stressing reinforcement at load transfer and at service load condition. So the reason for that is the reason for that checking at load transfer and at service load condition is for us to ensure that at service load, cracking is negligible and the long-term effects on deflection or camber are well controlled. So that is actually the reason why we usually check the prestress member that we are designing at load transfer as well as at the service load condition, because we want to ensure that there will be no cracking that will be experienced by the prestressed concrete members uh, along the lifespan of the member itself. So that is the main reason why we are conducting pre-stressing on the concrete element, because we want to control the tensile stresses that will be experienced by the element as it supports the intended loads that it is supposedly to be carried, or that is supposedly to be carried by it, because we know for a fact that those external loads that are being experienced by the concrete element tends to produce what we call tensile stresses on the concrete element. And we know for a fact that concrete has a very low strength to resist tensile stresses. So due to that, we want to assure that uh, the tensile stresses that will be experienced by our concrete will be controlled, so that there will be no failure with respect uh, to the tensile stress acting on the concrete element, because we know that if the tensile stress acting on the concrete already exceeded the 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 strength of the concrete on resisting tensile stresses, we know that the result will be cracks, and any cracks that is being produced in a concrete element tends to uh, propagate gradually along the concrete itself, that may result to total failure of the concrete element itself. So we don't want that scenario to happen. That's why we are checking and ensuring that at service load, cracking is negligible. That's why we are conducting additional checks at load transfer and at service load condition, in addition to the checking of the strength of the prestressed member that we are designing at failure, or at its ultimate uh, at at its ultimate strength condition. So a logical sequence in the design process entails first the service load design of the section required in Flexure, and then the analysis of the available moment strength Mn of the section for the limit state at failure. So usually this is the logical sequence in the design process of uh, pre-stress members in terms of flexure. So first we have to check its capacity uh, to resist the service loads that are expected to be carried by the member itself. And then after we have found the the particular section that is sufficient enough to address the flexural requirements, we will now analyze that section that we already found out that satisfies the flexural requirements. We will just analyze its available moment strength to resist the ultimate flexural stresses at failure. So that is usually the logical sequence in the design process of pre-stressed concrete members. Again, the design process starts with the service load design, wherein we are checking the service load requirements specified by the code, especially the requirements in terms of flexure. So after we already found out a particular section that satisfies the flexural requirements, we will analyze its available moment strength to resist the flexural stresses or flexural requirements at failure, or the ultimate flexural stresses that may be induced inside the concrete element uh, at failure stage, at ultimate strength stage. So uh, again, the ultimate strength design stage of the design of Prestressed concrete members are somehow similar to the design of reinforced concrete members. So if you can see, one of the most important part of designing a Prestressed concrete member is to check its design with respect to the service loads, or in other words, the service load design of the section. So uh, that is what we will focus on this discussion, the service load design of the pre-stressed concrete members that will satisfy the flexural requirements.